Hi everybody, here we are at the very end of chapter 4, Algebra 2. We're looking at 4.8 and we're going to use matrices to solve systems of equations. And I know we've done that before in terms of the Cramer rule, but we're going to do it in a different way. Our vocabulary is matrix equation, and we're going to talk about what that means by using a little. Suppose we had a system of linear equations like this, typical, we've seen it before, we've seen it all throughout this chapter. We could use something called a matrix equation, which is this. Let me see if I can find it. There it is. Back again. Gone and back. Gone and back. Let's see if I can get it to come out. All right. The matrix equation, I'm going to slide it over here. You can kind of see it. The matrix equation, there it is, would be, you're going to take the coefficients here, 5, 7, 3, and 8. 5, 7, 3, 8. You're going to make what we call a coefficient matrix. That will be A. Then XY will be the variable matrix, and then B will be the constant matrix, which happens to be kind of like the answers. And what I want you to observe is that if you were to multiply these matrices together, 5, 7 times XY, 3, 8 times XY, you would end up with this situation here. You'd actually end up with the system of linear equations that we have. Does that make sense? So when you're asked to create what we call a matrix equation, you're going to create an A times X equals B situation where you've got the coefficient matrix times the variable matrix equaling the constant matrix. Our first example requires us to do just that. We're going to write a matrix for the system of equations. So if you remember from the last example, or from the last situation we saw, we had the coefficient matrix. I'm going to write the numbers first: 5, negative 6, 3, and 2. And that we refer to as A. And we know that if we multiply it by the variable matrix, which we call X, and that literally is just X and Y, the variables, we will get the constant matrix, which I still want to call the answer matrix. Negative 47, negative 17 will be that matrix. And I think they use B as the variable. So A times X equals B. And that's all we're doing here. This next example, though a little bit more involved, is really going to be just as simple as the last one ultimately. So let's take a look. In chemistry, the molecular formula for glucose is C6H12O6, which represents that a molecule of glucose has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. One molecule of glucose, I can't say the word, weighs 180 atomic mass units, or AMUs, and one oxygen atom weighs 16 atomic mass units. The formula and weights for glucose and another sugar, sucrose, are listed below. So you can see here that the weight of this molecule would be 180 AMU, and the weight for this molecule would be 342 AMU. So we're going to write a system of equation that represents the information that we have here. So the system would be if you had 6 carbons plus 12 hydrogens plus 6 oxygens. I'm going to make my O a little fancy. That would equal 180. And then if we had 12 carbons plus 22 hydrogens plus 11 oxygens, that would be 342. I don't know about you, but when I see a system with 3 variables, I want 3 equations. And we do have one in here. We were given the fact that oxygen is equal to 16. And so what we then can do is, if we wanted to, we could look at this as a system of 3 variables in a system, a system of equations with 3 variables, or we could make it a system of equations with 2 variables. And things being what we know, when you get into a 3 by 3 matrix, things get a little bit difficult. So let's go ahead and make this a situation where we only have 2 variables, C and H, since we already know what oxygen weighs. We're going to plug in 16 for oxygen and then change our equations a little bit. Once I have this, I multiply 6 times 16 here, and then when I subtract that from 180, I'll get an equation where I only have C and H. Similarly, once I multiply 11 times 16 and subtract from both sides that product, I'm going to have an equation where I just have C and H, and that's going to make life a lot easier for us. So using that calculation, we get these two values or these two equations as our system. And finally, we already know how to write a matrix equation. We're going to write our coefficient matrix times our variable matrix times our, well, is equal to our constant matrix, which basically is the answers. And then this is our result. This is what we get. So not too bad. And remember, this one is A, and this one is B, and this one is, oh, no, just made that up. This one is A, this one is X, and this one I think we had is B. All right, so, we need to figure out how to use this wonderful way of rewriting our system of linear equations. How do we use that to solve an equation? And we're going to talk about that with this example. Example 3 says, solve a system of equations, and we're going to use a matrix equation to solve it. So, we're going to have to start off by putting it in matrix equation form. So this is our result, which is the matrix equation form. Fine. Now, we're going to consider this analogous relationship that the text has for us. So the text says that if we look at these matrices as A times X equals B, right? A times X equals B. What would we do if this were like a regular equation, right? What would we do? We would try to get rid of, because we're solving for X, we try to get rid of the A value. And so to get rid of the A, we need to, in a way, use the multiplicative inverse to come up with the multiplicative identity, right? We're trying to get rid of it so that this whole situation can become 1. And what we do to one side, we do to the other. So we multiply both sides by 1 over A. We get 1 times X, which is essentially X, and we've now solved for X. We're going to do the same thing with our matrices. With this solution matrix, or this system of equation matrix, we know that we've been talking about this as AX times B. AX is equal to B. So we'll multiply both sides by the inverse. And order matters, so we need to make sure and multiply it by the inverse of A times X. We know that's going to give us the identity matrix times X, which basically is just going to give us X, and we'll have the values. I kind of like this. We'll have the value, or the answer for our problem. We'll have the answer here. So let's do that. So I've rewritten our matrix equation down, right? Our matrix equation. And what I'm going to do is on this side, let me do it in a different color. I need to put the inverse, right? And then on this side, I need to put the inverse. And so what's the inverse of this matrix? You remember from the last section, we do 1 over the determinant, in this case, of A, times this thing. We're going to switch these guys. Switch -8 and 6, and then change the signs on these guys. -3 and -2. What's the determinant of A? Well, it's going to be 6 times -8, which is going to be a -48. -48 minus 6. -48 minus 6 is going to be -54. Let me try that one more time. Yeah, I believe it's -54. So that -54 becomes my denominator. And when I multiply everything, I get this really tiny. I wrote it really small, but I'll get a +8 over 54 because the negatives cancel. 3 over 54, positive 2 over 54, and a -6 over 54. When I multiply these guys together, I will definitely get, you know what I'm going to get? The identity matrix, right? Because that's the goal. That was the goal, and that's what's going to happen because they are inverses of one another, right? That's my expectation, and that's what will happen. And so I'll get the identity matrix times, let's do this in black and a little bit thicker, times the variable matrix. And then when I multiply these two together, right? And so you remember we're going to do across and down. We're going to get a matrix that is 2 by 1, right? Which is going to be perfect because then I'll know exactly what X and Y is. So then I get 90 over 54 and 27 over 54. So that tells me that X is equal to, I'm going to reduce this, 9 goes into both of them. 9 goes into 90, I guess 18 actually does. 18 goes into 90 5 times, and 18 goes into 54. 18 goes in 54 three times, so I get 5/3. And these guys are related to each other because 27 goes into both. Y is equal to 1/2. And so that's my answer. This is kind of a neat way, right, to solve systems of linear equations, maybe a little better than Cramer's rule. I don't know. Example 4 gives us an opportunity to consider what would happen if we had a situation where there was no solution. So again, we're going to set up our matrix equation as we did before, and that is this. And in this case, it's AB and negative 18 and a positive 24. And what I'll do is I'll separate this out a little bit so that I can leave room for my inverse matrix. And so we know with the inverse matrix, the A inverse needs to go here and here. And the inverse matrix, again, is 1 over the determinant. And the determinant in this case, let's do that, is going to be 6 times negative 12, which is negative 72, right? Minus, so let me write it down, negative 72 minus negative 72. And you already see what the problem is. We get a 0 in the denominator times whatever matrix this is, doesn't matter, 1 over 0 times whatever this matrix is. This lets me know that the inverse doesn't exist, and therefore there is no solution. So we don't even have to go far. That's kind of nice, right? Not going too far. Look, that's the end of our lesson. Let me know if you have any questions or concerns. We can look at them. Hopefully the work isn't too onerous, isn't too much. If you feel like it's overwhelming, let me know and we'll see if we can pare back some of the problems. Also, we should be looking at preparing for a test in all of Chapter 4. And so we can get Chapter 4 behind us and move on to Chapter 5. Look, take care. It's been a pleasure. Look forward to talking to you soon, sweethearts. Bye-bye.